the flexible pavement thickness design methods. As per the syllabus, we have three methods. One is Asphalt Institute method. Another one is AASHTO method. Third is IRC method. Anyway, IRC method has already been completed in transportation engineering one. So I will try to solve one numerical problem on IRC method. Now, before we begin the design methods, first we'll see about the flexible pavement, its component layers, and the functions of each component and other things. Now, all of you know about the cross section of conventional flexible pavement. Now, this pavement is comprised of so many layers. If you see from the bottom, there will be natural subgrade and compacted soil subgrade, and over that we provide subbase course, and over that we provide base course, and then there will be binder course and surface course. These many layers will be provided on natural soil subgrade, where the natural soil subgrade is in loosest condition. Now, there are different materials we generally use for different materials, and this is a multi-layer pavement. It is flexible in nature. It has a flexural strength of 0, and the quality of the flexible pavement is decreasing with increasing depth. These concepts have already been discussed. Now, if you see the materials used in the flexible pavement, now see the first one, the cleaning and graveling, overall ground level, and over that we provide embankment. Embankment is just a soil and subgrade soil, and over that we provide subbase course, and then we provide wet mix macadam, then we provide binder course in the form of dense bituminous macadam, and then we provide bituminous concrete mix. Right. Now, if you see the principles of flexible pavement design, the pavement structure is considered as multi-layer elastic system. Yes, you know, and the materials we use in various layers may be characterized by elastic modulus or resilient modulus. Now, subgrade is infinite in both the vertical and horizontal direction. This is the assumption. And other layers which are laid over the subgrade are finite in vertical direction but infinite in the horizontal direction. Now, we assume the maximum vertical stress occur directly under the wheel load. The nature is compressive. The stress intensity will decrease with increase in depth. The maximum horizontal stress occurs directly on the under the wheel load, but it may be tensile or compressive in nature. Generally, the flexible pavement is designed based on strength criteria. There may be chances of excessive cracking of the asphalt course, the wearing course, and there will be permanent deformation of subgrade. So, rutting and fatigue criteria we generally consider. So, these are the methods we consider in the pavement design. Asphalt Institute method, AASHTO method, IRC method. Now, Asphalt Institute method. First, we'll discuss about Asphalt Institute, then we go for AASHTO and IRC method. Now, this is an elective course of BTech final year, and it is very important to develop the theory of pavement design methods by knowing the nomograms or design charts and its usage. So, you are requested to concentrate on how to develop the theoretical aspects of these design methods. Okay. Now, first we'll see Asphalt Institute method, but for the design of any pavement, either it is a flexible pavement or rigid pavement, we must need some data. The data generally composed of traffic data, climate or environmental conditions, material data, and other data include construction, cost, maintenance, design period, etc. Now, if you see the traffic, now we have used different terms in different methods of analysis, CBR method, and there are IRC methods, there are group index methods, and so on. So each method has its own limitations. So the traffic data may be used depending upon the method used. Okay. As far as this Asphalt Institute method, we consider the axial load magnitude of axial load, usually expressed in terms of equivalent standard axial load, its volume, how many number of vehicles, its composition, single axle, tandem axle, tridem axle, and so on, and the tire pressure, contact area. Now, usually the axle load is expressed in terms of some standard axle load, expressed in terms of equivalent single axle load of 80 kilonewtons or 18,000 pounds, usually expressed in terms of 18 KIPS. The total number of equivalent single axle load is used as a traffic loading input in the design of pavement structure. So the design traffic intensity is calculated through the life of the flexible pavement, and that is used as traffic loading. That is the important parameter needed for this flexible pavement design. Then environment, yes, we need temperature variation, and also we consider moisture, as the temperature and moisture are affecting the pavement performance. Now coming to the material characteristics, yes, there are different types of materials used in the construction of flexible pavement. If you see from the top, there will be asphalt surface, that means bituminous surface. Then below that, there will be base course, granular base, granular sub-base course, that means we use aggregates of different sizes. And there is subgrade, we lay the subgrade on the natural soil. Okay. Now, these are the three kinds of materials we generally use in the construction. Now, when you see the asphalt surface, very strong, good quality material is used, and its elastic modulus is higher when compared to all other layers elastic moduli. Next will be granular base and sub-base elastic moduli. Next is subgrade. Now, we express the strength of these materials in the form of subgrade soil strength is expressed in terms of CBR, or sometimes it may be expressed in terms of resilient modulus or elastic modulus, or in terms of shear strength. Similarly, granular base, sub-base course, its strength may be expressed in terms of CBR or resilient modulus, and the asphalt surface course, that is top surface layer, its strength is expressed in terms of Marshall stability. But in most of the cases, the strength of any pavement material can be expressed in terms of CBR value. So if you know the CBR value, then we can find the resilient modulus. As Asphalt Institute method and AASHTO method generally use resilient modulus MR in the design. So this resilient modulus MR may be expressed in terms of pounds per square inch PSI or megapascals, whatever be the unit. You can use this relation to calculate MR of any pavement material, knowing the CBR value of that material. Now, in today's class, we use the CBR value of the soil subgrade expressed in terms of percentage, and MR is expressed in terms of PSI. Therefore, remember the resilient modulus of subgrade soil is equal to 1500 times CBR value. So these are material characteristics. Now, Asphalt Institute method generally considered two assumed stress strain conditions. Yes, we all know about the stress strain condition. Now, if you see this figure, now the load is applied to the wheel, and through tire pressure, the pressure is applied on the soil subgrade. Now, this is the topmost layer of the pavement, where the pavement is experiencing maximum vertical stress here, and as the depth increases, the vertical stress is going to be decreased until the vertical stress is lower than the subgrade soil strength. That is one assumption. And see the second one. Now, when the load is applied to the wheels of the vehicle, under the low wheel, the pavement material undergoes deformation. See this deformation. Yes, this is the deformed shape of the flexible pavement. Yes. Now, the bottom fibers are in tension. Now, this is bottom fibers are in tension, but the fibers under the wheel load will be under compression. But beyond the load application surface, the top fibers are in tension, the bottom fibers are in compression. Now, the Asphalt Institute method, we generally consider two strains, yes, as I mentioned, fatigue and rutting. Now, in the case of first fatigue cracking, the horizontal strain ET is developed at the bottom of the asphalt layer. Asphalt layer is the bituminous concrete layer of considerable thickness. At the bottom of that layer, this horizontal tensile strain is developed, and we need to limit the horizontal tensile strain while designing the flexible pavement. This failure is said to be fatigue cracking. Okay. Now, there are other chances of failure of flexible pavement, that is due to the vertical compressive strain exceeding the deflection of the subgrade known as rutting. So we need to consider these two failures, right? So this ET and EC are considered as failure criteria. We need to keep both strains should be within the limits. Therefore, any flexible pavement can be designed based on two criteria. One is fatigue and other one is rutting. Now, the design procedure, yes, it is very important to understand the design procedure of Asphalt Institute method. Asphalt Institute method developed the design methodology for the flexible pavement design for different combination of layers, right? So different layers are used: asphalt concrete layer as surface course, and base courses, maybe soil sub-base course and base course. We use different materials. Therefore, this Asphalt Institute method provided several charts to design the flexible pavement thickness. Okay, there are 6 charts developed by Asphalt Institute for different pavement structures. Okay, 6 combination of pavements. Okay, you just see the first one. There will be full depth asphalt concrete. Okay, there is one chart, and asphalt concrete surface and emulsified asphalt base. Now, two categories of pavement material. One is asphalt concrete surface course, other one is emulsified asphalt base. Under this category, there will be type 1, type 2, type 3. So, an asphalt concrete untreated aggregate base. Another category. Under this category, there will be 2 more charts. Base thickness of 6 inches, base thickness of 12 inches. But however, to simplify the analysis or the pavement design method, we'll see full depth asphalt concrete using only one figure, and today's class is dealing with full depth asphalt concrete pavement thickness only. Okay. Now, in most of the university question papers where you are asked to write the design procedure of Asphalt Institute method, you just remember full depth asphalt concrete pavement design method. So we discuss only the combination 1, full depth asphalt concrete. Right. Now, anyway, we are just providing you the chart developed by Asphalt Institute. Just see the chart. So once if you look at the chart, first we see the axis names. Okay. X-axis, something has written on x-axis equivalent 18,000 lb, single axle load, equivalent single axle load. Yes, the traffic intensity, design traffic intensity is expressed in terms of equivalent single axle load. To calculate equivalent single axle load, we use some equations, some expressions. Okay, 365 into present day traffic intensity into 1 plus r power n minus 1 by r into vehicle damage factor into lane distribution factor, and so on. That expression is used here also. So that is x-axis. Okay, I can measure this equivalent single axle load. Yes, it is known to you. This is known to you. And see the y-axis, what has written subgrade resilient modulus MR. In one of the slides, I used M small r, but M capital R is also abbreviated for subgrade resilient modulus, PSI. Some of the charts available where MR is expressed in megapascals, or some of the charts are used in this particular discussion where the value is expressed in PSI. Yes. Now this chart is for full depth hot mix asphalt, HMA, hot mix asphalt. That means bituminous concrete in India. Bituminous concrete layer. Yes. Now there are various diagonal lines. Diagonal lines, one, two, different diagonal lines, mentioning some thickness value. 4-inch minimum, 5-inch minimum, 6-inch minimum, 7-inch minimum, 8-inch, 9-inch, 10-inch, up to 20 inches. That means the thickness of the hot mix asphalt or flexible pavement is varying from 4-inch to 20-inch. Now, I know the value on the x-axis, yes. I know the value on the y-axis, yes. By knowing these two values, I can read the thickness of asphalt pavement. That is the design procedure, right? If I know this one, for example, if the value of equivalent single axle load is, for example, this is 10 power 5, 2 into 10 power 5, 4 into 10 power 5. Okay. Now, if the equivalent single axle load is 4 into 10 power 5, I just draw a vertical line like this. Yes. And if the value of resilient modulus is this one, I draw a horizontal line. Both will intersect here. Will represent the this intersection point is representing the thickness of the flexible pavement, that is 6 inches or 6 point something, okay, 6.1 inch. So that is the use of full depth hot mix asphalt pavement design chart. Anyway, we'll discuss the design methodology after knowing the data given in the numerical problem. Yes, now we look at the numerical problem. Yes, the flexible pavement has to be designed for a certain length of existing carriageway road from the following consideration. Yes. Now, current traffic of 80 kilonewton equivalent single axle load is given as 0.95 into 10 power 5 equivalent single axle load per year. So, annual traffic is given as 0.95 into 10 power 5, already given as annual traffic intensity. But usually, the traffic is given in terms of commercial vehicle volume, maybe 2,500 commercial vehicles per day. Now, after knowing the commercial vehicle traffic, we can multiply it with 365, we'll get the annual traffic intensity. But here it is directly given as 0.95 into 10 power 5 as equivalent single axle load per year. The design period 10 years, okay. Construction period 18 months, 1.5 year, and traffic growth rate 7%. Here, CBR values are given as 5% for soil subgrade. Yes, the corresponding resilient modulus in terms of PSI is 1500 into 5, 7500. Now, elastic modulus of asphalt concrete for surface force 1500, and elastic modulus of base force 1200. Elastic modulus of subbase force 120. Now, if you see the elastic modulus values in terms of megapascals, but here resilient modulus value is given in terms of PSI. And the elastic modulus of surface force is higher, 2500, and base force 1200, medium, and subbase force 120. Now, design parameters. First step is you just calculate what is the design traffic intensity using this expression. N is the cumulative number of standard axles to be catered for the design in terms of million standard axles, MSCA. So here R is traffic growth rate, N is life of the pavement, A is the present day traffic intensity in terms of commercial vehicles per day, and D is lane distribution factor, and F is vehicle damage factor. So these values will be given to you. Now the present day traffic intensity is given in terms of ESAL per year. Then there is no need of multiplying the expression with 365. So 365 is removed. R is 7%, N is 10 years. What is Y? Construction period of 1.5 year, and from this expression is 1.59 to 10 power 6 equivalent single axle. Axles. 1.59 into 10 power 6. Okay, right. So traffic intensity is calculated. Now, if you recall the chart given, where the x-axis is N and the y-axis is given as resilient modulus, 10.3 times CBR value when the resilient modulus is in terms of megapascals, and MR is 1500 into CBR of subgrade, where MR is expressed in terms of 7500 PSI, pounds per square inch. So y-axis value is 7500, x-axis value is 1.59. So these two values are enough for us to design the thickness of flexible pavement in terms of asphalt concrete layer. Now see this one. Now on x-axis, you need to look at 1.59 into 10 power 6. That means 1.6, for example, 1.6. Now this is log graph, where it begins with 1000. 10 cube means 1000, 2000, then 4000, then reach to 10,000, 20,000, 40,000, then 1 lakh, 10 power 5. Okay. So in our case, the value is 1.6 into 10 power 6. 1.6 into 10 power 6. Now this is 10 power 6 value begins from here, and this will be 1 into 10 power 6, and this will be 2 into 10 power 6. This will be 3 into 10 power 6. Right. So 1.6 will be 1 into 10 power 6, and this is 1 into 10 power 6, and 1.6 will be this one. You draw a vertical line on 1.6 into 10 power 6. Now it will be like this, and see the MR value 7500 PSI, 7500. Now here it is 10 cube 1000, 2000, 4000, 5000, 6000, then 7000, and this could be 7500. Now from this point, draw a horizontal line onto this axis. It will intersect here. Now this intersection point denotes the thickness of the pavement. Now in this case, it intersects on the curve of 10 inch. Therefore, 10 inch is the thickness of flexible pavement. So 1.59 into 10 power 6 and MR of 7500 PSI. Full depth of asphalt concrete is 10 inches. So that is 250 mm. Therefore, the thickness of flexible pavement is 250 mm asphalt over subgrade of 5% CPR. Now, up to this, we calculated the total depth of the flexible pavement, but in terms of asphalt material. Now, this 250 mm is asphalt material only, but the flexible pavement is comprised of asphalt layer thickness, base course thickness, sub-base course thickness, and so on. So 3 layers, but here 250 mm is expressed in terms of only asphalt layer, but we won't provide 250 mm asphalt pavement in the construction of flexible pavement, right? So now we need to divide this 250 mm asphalt layer into 3 layers. One could be asphalt layer of some minimum thickness, other layer could be base course, and other layer is sub-base. Now this is sub-base, this is base course, and this is asphalt layer. But the Asphalt Institute method provides us the thickness in terms of asphalt layer thickness, 250 mm asphalt. Okay. Therefore, the next step could be calculation of individual layer thicknesses. Okay. Individual pavement layer thickness calculation. Next we'll see. Right. Thickness of wearing course, but usually the wearing courses we just provide a minimum thickness of 75 mm, 3 inch. Okay. So let us assume thickness of wearing course 75 mm. Okay. Now this is thickness of wearing course 75 mm. But what is the total thickness? Already calculated in the previous step, 250. So 250 minus 75 will be 175 mm. Now this is remaining thickness of asphalt concrete. Thickness is T. RAC means remaining thickness of asphalt concrete. Remaining thickness of asphalt concrete is equal to 175 mm. Right? So first layer thickness is assumed as 75 mm. So first component layer thickness is over. Next we go to the next step. we calculate the base course thickness, of base course. The next layer thickness is base course. Yes. Thickness of base equivalent to thickness of remaining asphalt layer can be calculated by relation. Now you just remember this relation. Yes. Thickness of base course divided by remaining asphalt concrete thickness equal to elastic modulus of asphalt concrete layer, elastic modulus of base course concrete layer power 1 by 3. Now this elastic modulus of asphalt layer is given in the problem. Elastic modulus of base course concrete is given in the problem. Then this remaining thickness of asphalt concrete is already calculated in the previous step. Now only unknown is PBC. Now, thickness of base course is equal to 175, that is this one, multiplied by 2500 by 1200 power 1 by 3. Works out to be 223.51 mm. What is this? This is thickness of base course, below the wearing course of 75 mm. Okay. But anyway, we won't provide this thickness directly as base course material, because we also provide sub-base course below that base course. Therefore, you can divide these 223 into two layers by assuming minimum base course thickness of 100 mm. But in our example, minimum is 100, so I am assuming 120 mm as the base course thickness. Therefore, remaining base course thickness is equal to 223.51 minus 120, that will be 103.51 mm. So, as of now, the cross section of the flexible pavement is wearing course 75 mm, thickness of base course I assume it as 120 mm, and the remaining thickness of base course 103.51 mm. But however, there is one more layer thickness is pending, that is thickness of sub base course. Then we'll see how to calculate the thickness of sub base course. Right. Now thickness of sub base course, because I know the elastic modulus of sub base course, elastic modulus of base course, then thickness of sub base course can be calculated by using this expression. Now in this expression, remaining thickness of base course is known, this is known, and this is known. Therefore, thickness of sub base course is equal to 103.51 into 1200 by 120 or 1 by 3. So it is 223 mm. Right. Now the final pavement thickness is wearing course 75 mm. We assume, yes, base course thickness minimum is 100 mm, but we assume that it has 120 mm. Now the balance sub base course thickness is 223 mm. Now if you see the total thickness, it is equal to 223 plus 120 plus 75. But in the first step, we calculated total thickness, but in terms of asphalt concrete as 250 mm. But here, the 250 mm asphalt concrete costly material is going to be divided into 75 mm asphalt concrete, 120 mm granular base course, 223 mm granular sub base course, and laid over soil subgrade of 5% CBR. This is the Asphalt Institute method. Very simple to calculate the individual layer thicknesses and to read the thickness of total flexible pavement. So I request you just prepare a theory on the pavement design method using Asphalt Institute method. Okay, develop a theory, step-by-step procedure of Asphalt Institute method after going through the numerical problem. So you may expect numerical, one of the questions in the examination as a theory. Develop the step-by-step procedure of Asphalt Institute method. Okay, so you know the data to be used in this method, and you know the design steps, and you know the chart to be used, and so on. Next, straight away we move into the AASHTO method of flexible pavement design. You heard about AASHTO in the rigid pavement design, where we used AASHTO design of rigid pavement techniques. Now here, AASHTO also developed a flexible pavement design method. Now directly we go to the numerical problem, where the figure below is a pavement system with resilient moduli given, layer coefficients given A1, A2, A3, M2, M3, and drainage coefficients M1, M2 or drainage coefficients, and equivalent single axle load already given as 6 into 10 power 6. Reliability 95%. You know about reliability. This is the confidence level of on the design. Then this is standard deviation, okay, and delta PSI, pavement serviceability index, and you are asked to design what is D1, D2, and D3. That means thickness of flexible core. Okay. Now this is the topmost layer, obviously asphalt concrete. This is base course, and this is sub-base course, and all these three layers are laid on the soil substrate. Now, for the design, we need some data. Okay, the data may be in terms of traffic. Okay, the traffic intensity here directly given as 6 into 10 power minus 6, 10 power 6 equivalent single axle load. So the data traffic factor parameters are given to you. Next, the parameters related to the pavement material quality. Now here E1, elastic modulus of the surface force, elastic modulus of base force 30,000 psi, 4 lakh psi, E3 is 11,000 psi. So elastic modulus of pavement layers. And if you see the subgrade resilient modulus 5,700 psi. Yes. So the pavement material quality also given. The drainage coefficients and layer coefficients A1, A2, A3 are also given. So only thing is you are asked to calculate what is this D1, what is this D2, and D3 using this method. So we'll see the calculations in the subsequent slides. Now, and as you just see on this side, there are some terms mentioned: SN1, SN2, SN3, structural numbers of layer 1, layer 2, layer 3. We'll see. Now, first we determine what is this SN1, SN2, SN3 from the graph. For the given 95% reliability, standard deviation of 0.35, and design traffic intensity of 6 into 10 power 6 ESE, and delta PSI of 2.1. Okay, right. Now this SN1, SN2, SN3 are calculated based on elastic modulus as resilient modulus, E3 as resilient modulus, and roadbed soil, that is subgrade soil elastic modulus, that is resilient modulus. We calculate SN3. Okay. Now SN1, this E1 is considered SN1, E2. SN1, E2 is considered as the resilient modulus while calculating the SN1. While calculating SN2, E3 is considered as resilient modulus, and SN3 is calculated using subgrade resilient modulus. So the resilient modulus of the below layer is considered while calculating SN1, SN2, and SN3. Now for all these cases, SN1, SN2, SN3, we consider 95% reliability, 0.35 standard deviation, and traffic intensity of 6 into 10 power 6, and delta PSI of 0.1. Now just observe this design chart given as AASHTO flexible pyramid design nomogram. Observe this nomogram. We just begin it from the left side as usual. Okay, there is a vertical axis, reliability axis. Yes. Okay, R percentage begin from 50%, 60, 70, 80, 90, 99, and 99.9. Then there is overall standard deviation axis. This is the inclined axis of standard deviation. Now it is given in our problem. There is a turning line. This could be the first turning line. And then first turning line, and then estimated traffic intensity, the vertical axis, yes, begins from 0.05 to 50 into 10 power 6 equivalent standard axles, and again there will be another turning line. Okay. Then the next vertical line axis is effective roadbed soil resilient modulus, that is soil subgrade MR, yes, known to us. And then there is a chart of design serviceability loss delta PSI, design structural number SN. So this is unknown in our case, and this is design serviceability loss delta PSI, but expressed in terms of, given in terms of some curves. First curve delta PSI is 0.5, second curve 1, third curve 1.5, 2, 2.5, 3. These are the curves denoting the delta PSI. Okay. If you see this chart, the reliability percent is known to you, yes, and the standard deviation is known to you, then traffic intensity is known to you, then effective roadbed soil modulus of resilient modulus is known to you, and then delta PSI is known to you. Then only thing is you need to read what is this design structural number. This is the only. For example, see this. W18 is 5 into 10 power 6. That is traffic intensity. 5 into 10 power 6. Then R is equal to 95%. Reliability is 95%. Yes. Now this is 95%. Then standard deviation is 0.35. Yes. Now this is 4, and this could be 0.5%. And MR is equal to 5000. Now this is MR 5000. Delta PSI is 1.9. So 1.9 could be closer to 2. This curve may be taken, and you are asked to read what is this structural number. Right? So I begin with 95% reliability. I will draw an inclined line onto the standard deviation axis, and it will be extended onto the first turning line, and then from this intersection point of the first turning line, I'm going to draw another inclined line onto the traffic axis, where the traffic axis is 5. So this is the inclined line 5, and then from it is going to be extended to the next turning line. From the next turning line, again I am going to draw an inclined line onto the resilient modulus of soil subgrade, and it is going to be extended onto the chart. Okay. Then from this intersection point, I will draw a horizontal line onto the delta PSI curve. Now this is the delta PSI curve. From this intersection point, I am going to draw a vertical line onto the structural number axis, which will directly give us 5 as a structural number. 5 as structural number. Now, very simple to read what is structural number. If I know the structural number, I can calculate the depth of each flexible pavement layer. Right. Right. SN1, SN2, SN3 is going to be calculated. For that purpose, you need to know about MR of soil subgrade, then MR of base course, MR of subbase course. Right. Now SN3 is calculated using MR of soil subgrade. SN2 is calculated using MR of subbase course. SN1 is calculated using MR of base course. So those 3 MRs, that is resilient modulus, are noted here. Okay, and the reliability for all the cases 95%, standard deviation for all the cases 0.35, and the traffic intensity for all the cases same, and the only unknown and also delta PSI is 2.1 is same for all the cases. The only variable is MR of soil subgrade, MR of subbase, MR of base course. These 3 readings. So if you read all the 3, you can see the SN1 as 2.7, SN2 as 4.1, SN3 as 5.8. Yes. Now individual layer thickness can be calculated using the equation of D1, D2 and D3. Okay. D1 is equal to SN1 by A1. This is the empirical relation given by AASHTO. So SN1 already calculated as 2.7, and A1 is the layer coefficient given in the problem 0.42. Therefore, thickness of asphalt layer, that is top layer, is equal to 6.43. D2 is SN2 minus A1 D1 by A2 M2, where M2 is the drainage coefficient, A2 is the layer coefficient of second layer. A1 is the first layer coefficient. D1 already calculated in this expression. SN2 calculated from the chart. All are the known values. Then D2 is second layer thickness, base course thickness 8.23 inches. Then coming to the third layer, subbase course thickness is equal to SN3 minus A1 D1, A2 D2 into M2, A3 and M3. Now here A1, A2, A3 are layer coefficients, M2, M3 are drainage coefficients given in the problem, and D1, D2 already calculated. Therefore, SN3 is the structural number 3 calculated as 5.8. So from this expression, E3 is equal to 70.71. So finally, draw a cross section of the flexible pavement indicating S1, SN1, SN2, SN3 on this side, corresponding D1, D2 and D3 on this side. So surface force first layer, base force second layer, subbase force third layer, and this is road bed soil survey to draw the cross section. Simple, but the only thing is you need to remember the equations. You need to read how the structural numbers are read from the design. So in this case also, I'm expecting the theoretical question from flexible pavement design. So develop the theory of AASHTO method of flexible pavement design. So finally, IRC 37 2012. So we have already discussed in the previous semester IRC 37 2012, but quickly go through the numerical problem of IRC 37 2012. Now, hot mix asphalt, as I said, is a flexible pavement. In India, we call it as bituminous concrete pavement, BC pavement, or asphalt concrete pavement, AC pavements. Now, it is flexible since the total pavement structure reflects under the load application. So, in India, 82.2% of roads are flexible pavement, and loads are transferred to layers, multi-layers. Now, IRC design method is the CBR value of soil supply. Now, you know about this expression of cumulative number of standard axles. N value is calculated using the expression. Already we have seen this expression. Now, see the numerical point. Design a highway flexible pavement for a design period of 15 years, and for the CBR value of 8%. The traffic flow data is given in the below table. Traffic axle load survey, 3 days they have conducted. Single axle vehicles, 2 axle vehicle, multi axle vehicles, day 1, day 2, day 3. Average daily vehicles given. So 1147 is the average vehicle. Light commercial vehicles. Now see the average traffic commercial vehicles per day 1964. So 15 years is the design life given to you. The data from axle load survey 1964 as the total commercial vehicles per day. 1964. Now from the IRC codebook, IRC 37 2012, we assume growth rate as 7.5%, vehicle damage factor as 4.5, and lane distribution factor as 0.75. Initial traffic intensity is equal to P into 1 plus R power X, where X is the construction period, 2 years, and present traffic intensity 1964, and traffic growth rate is 7.5%. Therefore, A value, initial traffic intensity, exactly at the 0 year of pavement is 2,270 commercial vehicles per day. Then cumulative number of standard axles, 365 into 1 plus R power n minus 1 power by R into A into F into D. So A is 2270, F is vehicle damage factor, lane distribution factor 0.75. So works out to be 73 million standard axles. If I know the million standard axle loads, cumulative number of standard axles, and CBR values of grade, using the design charts given in IRC 37, I can directly read the thickness of surface pores, base pores, and surface pores. This is the plate number 6 for 8% subgrade soil. There are more than 32 charts are available in the IRC 37 for different combinations of CBR value and different combinations of traffic intensity, right? So in our case, the traffic is between 50 to 100. It is obtained as 73 million standard axles. Okay, so I'm choosing plate 6 for soil subgrade CBR of 8%, right? Yes. Now see this chart, plate number 6. On this axis, pavement thickness is given in mm. On this axis, traffic is given in million standard axles. Okay, so this is 50 and this is 100 million standard axles. So my traffic intensity is 73. So it will be lying between 50 and 100. Okay. Then I know the thickness of different layers. Now the 73 may be here. I can draw a horizontal line on this in order to get the total pavement thickness. Total pavement thickness. Now total pavement thickness is 650. 650. 650. Now it is lying between 50 and 100. So it could be BC surface layer of 50, DBM of 115, wet mix macadam of 250, and GSB of 200. So straight away we can recommend this thickness. Surface force 15, binder force 115, base force 215, subbase force 215. So this is the thickness of flexible pavement using IRC 37. Now in this case also you are requested to develop the theory step-by-step procedure of the flexible pavement design using